this video, we're going to look at two concepts. Those are the gradients and directional derivatives in the plane. So to get started, we're first going to focus on gradients and gradient vectors. So I'm going to start with giving us a definition of what that gradient vector is. Then we're going to look at the preliminary example to start getting a geometric sense of this object. So the definition might look a little strange at first, but the more examples you see, the more comfortable and meaningful this definition will be. All right, so first of all, gradients. The gradient vector of a differentiable function f at a point, AB, and so again, we're assuming f is a function of two variables. So this gradient vector is denoted either grad f of AB or this upside down triangle gradient f of AB. And it's defined the following way. So the gradient of f at AB is equal to the partial derivative in the direction of x at AB in the I direction plus the partial with respect to y at AB in the j direction. Typically in our class, the notation that we'll use is this upside down triangle because it's a little bit more concise. All right, but let's look at this preliminary example where we're actually going to be computing gradients of a function. And then again, we'll look at some geometric pictures of how these gradient vectors look on a set of level curves to get a sense of what they are and a deeper meaning. All right, so let's get started with this preliminary example. So we're told the temperature at a point xy on a metal plate is given by the function t of xy, and it's defined here, 1 minus 1/4 x squared minus 1/4 y squared degrees Celsius, where x and y are both measured in centimeters. All right, so we have two representations of this function here. We see that we have the level curves of t on the left, and we have a graph of the outputs of our function for any given xy input. So a couple observations we can make. Well, if we're at the center of the plate, 0, 0, then we're at the highest temperature. And as we go out radially, our temperature of the plate goes down. And we see that here in the level curves as well. All right, so now we are asked to calculate the gradient of t and use your formula to fill in the following table, which is given here. We're then going to sketch these vectors on the diagram. So let's go ahead and get started together. And I'll set you up, and then I'll have you finish off the table. So in order to compute the gradient of t, we need the partial derivative of t with respect to x and with respect to y. So we saw that in the last section. So we can first compute the derivative with respect to x. So our function is 1 minus 1/4 x squared minus 1/4 y squared. So we're going to treat y just like a constant, and x is going to be the variable that we vary. So our partial with respect to x is just going to be negative 1/4 times, should be a fourth, negative 1/4 times 2 times x. So just using that product or that power rule there, which just becomes negative 1/2 x. And then the derivative of t with respect to y now is similar. And in the end, we just get negative 1/2 y. All right, so then we can use these two partial derivatives to write the gradient of t at the point xy is going to be given by 1/2 x times the I vector, the unit I vector, plus negative 1/2 y j vector. Let me rewrite that j so it looks more like a j. All right. So now what we want to do is fill in this table. So that means we want to compute those gradients at specific xy points. So let's do a few together. So if we want to know the gradient at negative 1, 0, I'm going to plug in negative 1 for x and 0 for y. So that would look like negative 1/2 times negative 1 I plus negative 1/2 times 0j. So that just becomes 1/2 I. So I can just put 1/2 I there for the gradient of t at -1, 0. All right, let's do one more together here. So let's look at when x is -2 and y is 0. So the gradient of t at -2, 0, well, that's just going to be -1/2 times -2i plus -1/2 times 0j, which in the end, the negatives cancel, the 2's cancel, will just be I, and our j is just 0. So this will just be I. So now what I'd like you to do is pause the video and finish filling in this table on your own. And when you're ready, we can go ahead and compare our answers. All right, so we plug in 1, we should be getting 1/2 I, or -1/2 I minus 1/2 j. 0 root 2 should be no I, but -√2/2j. And then when we plug in 0 negative root 2, we should be getting positive √2/2j. Okay, so now let's go ahead and plot or sketch these vectors on that level curve diagram. So if we're looking here first at -1, 0, we can first identify that point, that xy point. So we see the x here starts at 0 in the middle, and then y increases in the vertical direction. So this point is 0, 0. So then if we look for the point -1, 0, we go -1 this way, 0 up. So there's our point. What does that vector look like at that point? Well, it's 1/2 I. So it's going 1/2 in the I direction. So it would be this vector here. All right. So that is the gradient vector at -1, 0. So at -2, 0, we're over here. And what does that gradient vector look like? Well, it's just I. So now it's going a whole unit in the I direction. So it's a little bigger. So now what I'd like you to do is graph the remaining 3 gradient vectors. And when you're ready, we can compare our work. All right, so the next point, 1, 1, we can identify as this point P here. And our vector is -1/2 I, -1/2 j. So we're going to go down 1/2 and over 1/2 to the left. So our vector should look like this. For 0, root 2, we see that we have 0 in the x, root 2 in the y. It looks like we're up here at this point here. And what is happening with our vector? We just have a negative j component, which is around, we'll go about like that. So it's not quite 1/2, it's a little less than 1/2. Less than 1, rather. All right. And then that last vector, 0, the point 0, negative root 2, is going to be down here at this point. And our vector is positive √2/2. It's going to look something like this. All right. So now I'd like you to make some observations about these gradient vectors. Maybe some observations in how they relate to the level curves, or maybe their lengths. And let's write down a few observations together. All right. So what's our first observation we can make? Well, in regards to how the gradient vectors behave with the level curves, we can see that in each case, the gradient vector at a point is perpendicular to that level curve. We never see any gradient vectors going out this way or up that way. They're always perpendicular to the level curve. So I'm going to write that down. So first observation, the gradient vectors appear, we don't know it yet, but they look like it, appear to be perpendicular. I'm going to clear off some room here. Perpendicular to the level curves of T. And furthermore, what direction do they point? Well, they're all pointing into the origin, which for us at 0, 0, when x and y are both 0, the origin is actually the steepest, or the maximum of our curve, or of this surface. So they appear to be perpendicular to the level curves of T, and also points in the direction of the max of T, maximum of our function. All right, now you might need to clear a little room because I want to make one more observation here. I want to make an observation about the size or length of these vectors. So what do we notice about the size of them? So here we have a bigger one, here's smaller. These two are the same size. This one's about the same size as these. Well, one observation we can make is that the gradient vectors appear to be longer where the level curves are closer together. So here the level curves are fairly close, while here we don't even see them. So I'm going to write that down because we're going to see that is true. That is the case. And we're going to see some other examples of it. So the gradient vectors appear to be longer where the level curves are closer together. All right. Well, great work working through this first preliminary example. In the next video, we're going to look at part B of this example.